Hello guys, this is Professor Perez here. I wanted to make a short video to talk about a few misconceptions that I think were lingering from the discussions of the discussion one forum way back when we did this. All of these stem around confusion about the scientific method. Now, some of these, I took notes, and some of these I wasn't entirely clear or certain that the problems that I saw were from inaccurate use of language, or if there were truly lingering misconceptions or incorrect ways to think about how science is done. So if we see here are my notes, and three main things here, and interestingly, they all had to do with science from this set of topics. Some of you did not choose this topic to talk about in your forum. But one, misconceptions around what hypotheses are. So they are not merely guesses, okay? Not just guesses. I want to bring attention to this slide here that I have. It's figure 1.12. Let's see the whole thing here. All right, 1.12 from your books. So if you have that there, you can open it. Okay. And so if you see here that this is a cycle, the scientific method is a cycle. Now, scientists not always are involved in all of these steps of the cycle. Why is this animated? Okay, anyway, you don't need all that. 1 second. Okay, that's weird. Okay, anyway, sorry about that. It's like doing its own thing here. Okay, so as I was saying, scientists don't always are involved in all of these steps. You can have scientists that devote their whole life to just making observations. You know, that's what exploration is all about. A very, very important part of the scientific method is the making initial observations or adding observations to something that's already known, a phenomenon that's been looked at. Okay, so very, very important. Now, some scientists are involved in all of these steps, as I mentioned, but not necessarily. So in terms of what an actual individual scientist is doing, could be in any one of these aspects or all of it. Okay, so if you look down here in the bottom right, formulate hypotheses, right? So a hypothesis is not merely a guess. It is based, you can think of it as an informed guess. I think that's the wording that I saw, an informed guess. So let's think about what do we mean by a guess? Okay, so if we think of hypothesis as a guess based on informed guess based on prior knowledge or observations, then that's somewhat okay to say, but I don't like the word guess because that kind of demotes the aspect here. So a hypothesis is based on observations, and also these observations, these hypotheses should allow you to make predictions that are testable. Okay, so they're not just merely guesses. You can think of them as informed guesses, but again, that would be not the best use of the term. They're a hypothesis. Sometimes we have a lot to go from, a lot of observations, a lot of data, a lot of prior knowledge. Sometimes we have very little. Even when we have very, very, very little, the hypotheses still take on sort of a logical set of situations. Well, and it's always going to be based on something. We've always been observing the environment from the day we're born, right? So it's hard to get out of that. But hypothesis could be based on logical potential things that could be going on. All right, so not just a random guess. Well, I guess this is what's happening, so let's test it. You could do that, but if you dig deep enough, you'll see that that guess is based on observations. We call that a hypothesis. And very important for this to fit in the scientific method, it has to be testable. You can make guesses or hypotheses about things that are not testable at all. That wouldn't constitute thinking in the scientific method, in the context of the scientific method. It's not science. All right. It has to be testable. Now, you can think of there's two issues here. Testable from a theoretical point of view. If we had unlimited resources, could you test it? If you could do anything, is it testable is the question. Now, practically might be very difficult or nearly impossible to test something because of limitations. There's ethical concerns. We can't do testing on humans. Things are really expensive. Some of our technology is limiting. We don't have the technology to do some things. So there's that. But as long as it's theoretically or plausible to be testable, then it is in the realm of the scientific method. Okay. I'm going to jump down here. Theories are a scientist's opinion. Well, what do we mean by opinion? Okay. This sounds a lot like a guess. Oh, my theory, this is just my opinion. It's an opinion based on a lot of scientific evidence. So these are theories. These are a little more robust explanations of the natural world. Yeah, I guess you can call them opinions, but an opinion sounds too random, it's whatever the scientist thinks is going to be. It's, not necessarily based on any data. That wouldn't be a theory. So these theories you can think of them as facts. Remember, in science, facts are always changing. Scientists could change their opinion, right? They could change their theories. I think everybody was clear on that theories can change. That's fine. That's great. Based on new data, new information, new experiments, results from new experiments, that sort of thing. But opinion sounds too wishy-washy. Okay, even though we understand theories can change, this opinion is too loose, too weak. It's almost like a guess. Okay, so that's not it. If there's two theories that are opposite to one another or slightly different, or two theories that there's equal support for, so we still don't know exactly which one is the strongest. We need more data at some point, right? If there's conflicting theories and hypotheses, a scientist could give his opinion or her opinion, what they think is the strongest evidence, But at that point, you're speculating. That would be, scientists do have opinions, right? But in terms of what constitutes facts in science, scientific facts, scientific knowledge, those are not just opinions. Okay, so at the point where a scientist begins to have real opinions, we call that speculation or arm waving, and something that's not backed by real evidence. Okay, so scientists try to avoid that. That's not a good thing to see in a paper. You could suggest future directions or potential things that could be interesting to test down the line. That's all fine. Okay. The second one here, life is too complex to be explained with scientific reason. Now, the sentence is life, right? So life sciences, biology, what we're studying here. So there's life, biology is a discipline of natural sciences. Natural sciences includes physics, astronomy, chemistry, that sort of thing, earth science, so forth and so on. Things that can be observed in our natural environment and observed with our eyes or tools, instrumentation, things that could be measured, things that are amenable to testing, that sort of thing. Yes, life is complex, but is it too complex? Can that complexity in theory not be captured in its totality. And now, in theory, scientific reasoning, that's why it's so powerful. In theory, scientific reasoning can understand the total complexity. Now, it's going to be very difficult to get it all, and it's going to take a lot of time, a lot of resources, more refined science and instrumentation and analysis, and right, to be able to grasp the whole complexity of life. So, life is not too complex to be explained with scientific reasoning. In theory. In practicality, probably, right? There's things in life that might be lots of variables, lots of moving parts, lots of things going on that would take very, very powerful computers and technology to understand it completely. It's sort of like weather. Weather is not life science, and there's things in biology that are equally complex for sure. But a good example that we can see every day is weather. Weather science has gotten really darn good at explaining how weather works. And we understand it quite well. But there's a lot of variables, and it's very difficult to understand it all. Now, I think in terms of weather science, for example, we understand the complexity really well, almost completely. We understand the complexity. That doesn't necessarily mean that we can predict the weather, because there are things that we understand about how the weather behaves that are basically unknowable because of something you might have heard, chaos theory, right? Chaos. There are some aspects that are potentially beyond knowing in terms of predicting what the state of a system will be in the future. So prediction might not be attainable 100%. We can get pretty close because of this phenomenon that at small scales you have chaotic events. And I don't understand the chaos theory really well, but I grasp the basis of it, that there is randomness that we can explain, but we can understand that there's randomness. Right? So we can explain the complexity, and some aspects of that complexity might be based on randomness. And we cannot predict randomness. See the thing there? So we can understand it, but that doesn't mean that we can predict the behavior of very complex systems, such as a cell, all right, or the weather. Okay, guys, so I hope that helped clarify a few details about the scientific method. And I'll be putting out some more videos tackling problem areas based on the Learn Smart results and the exam results from exam 1 and the future exam 2, so forth and so on. So look for these little mini lectures and let me know what you think.